Hello everyone, welcome back to the new improved online version of Computer Science 220 Data Programming. This is lecture 23 and would have taken place on March 13th if the school hadn't been closing down on us. Okay, so we're going to begin learning about recursion. This is the first of three sort of fancy techniques that we can apply to functions. Also, if you didn't get a chance yet to go back, make sure you go back to lecture 22 on our schedule and watch the short 10-minute video that reviews the three different options for copying data in Python. So today, I want to get started with a little review to put this lecture in context for the whole course, just to show where it fits in. So this is the second part of three. This 5-week section began with lists and dictionaries. And with these two data structures, we can pretty much solve any data problem that we're going to run into. Then, our data sometimes arrives as files. So we talked about CSV and JSON files. CSV files correspond to lists of lists, and JSON files can pretty much contain any weird combination of lists and dictionaries and strings and integers that we want. Okay, then we dove into what I think is the most technically complicated section of the course, objects and references. Time spent thinking about Python's memory model and how it arranges objects and has references to those objects stored in variables is well worth spending some time on. It's going to save you as much time as you spend studying in debugging your code later, trying to figure out why it works, and how to take advantage of that so your code runs more quickly. Okay, then today, like I said, we'll be beginning a discussion of three of the fancy techniques we can apply to functions. The first, recursion, is just functions that call themselves. The second one is generators. These can be thought of as functions that return some data but continue running. And then we'll find that functions are actually objects. That means we can have references to those objects, references to functions, and store them in variables. We can pass functions to other functions. And then to wrap up this section, we'll conclude with some conceptually much simpler topics, files and errors. Okay, let's jump into recursion. So a recursive function is one that can call itself. So this sort of self-reference is where I want to begin. And the goal is to use self-reference in a meaningful way. I've got a couple of examples here. The first one, Hofstadter's law. It always takes longer than you expect, even when you take into account Hofstadter's law. So this is a definition that uses the term Hofstadter's law in the definition. And yet, this one still makes sense. So it's meaningful, and that's the goal. If we take a look at my second definition down at the bottom, dialectic materialism is materialism that involves dialectic. If you don't know what dialectic means, or you don't know what materialism means, this is meaningless. I picked it because I had no idea what those terms mean. I looked it up, and if you're actually interested in philosophy, you can pause the video and read that right there at the bottom. But I'm going to continue on. We'll also find that self-reference doesn't necessarily take the direct path where the definition uses the definition, but can also be circular. Got an example of that here. A mountain is a landmass that projects conspicuously above its surroundings and is higher than a hill. Well, if you didn't know what hill is, you go back to your dictionary and you look that up. A hill, a usually rounded natural elevation of land lower than a mountain. Oh, if you don't know what mountain means, we go back up. And look that definition. Mountain, a landmass that projects conspicuously. Yep. If you're a computer, this is a real problem. You're going to end up in a loop that goes on forever. As a human, we can recognize right away that there's a problem here and go look for another source for definitions. Okay, so as we go into recursion, I want to break the rest of this lecture into two pieces. We're going to talk about definitions and recursive information. And then we're going to go into actually writing recursive code. Please go ahead and take a look at Chapter 5 and Chapter 6 of Think Python and read those sections appropriate to recursion. Okay, we just had several examples of recursive definitions. Hill, mountain, Hofstadter's law. These are definitions that contain the term in the body of the definition, even if it's circular. We're also going to find that recursion is very commonly found in dictionaries and mathematical definitions. So as an example here, let's take a look at the definition of a positive even number. We're all familiar with numbers. You had to graduate from high school to end up in this course. So We know that 3 is not a positive even number. -2 is not a positive even number. But 2, 4, 6, 8, those are all positive even numbers. So I'm going to take a little bit of a weird look at this. So I come up with a recursive definition. X is 2 is a positive even number, or X is a positive even number if it's equal to another positive even number plus 2. Okay, so 2 is a positive even number. It tells us right there in the definition. We also know that 4 is a positive equal number because it's equal to another positive even number. Right there, that would be 2 plus 2. Same way, 6 is a positive even number. It's equal to another positive even number, namely 4, plus 2 more, and so on. This is a definition that will get us all positive even numbers. So that's a mathematical definition. We're also going to find that recursion occurs in dictionaries, lists, and data structures. So a recursive structure is an example would be a list containing lists. If we look at this example rows here, I've got my square bracket that makes it a list. The first entry is a list. There's the second square bracket. This one contains the character A and another list. So this list containing the numbers 1 and 2 is actually basically 3 levels deep. I've got to follow 1, 2, and 3 arrows to get to this list. And there's no limit to how many lists I can nest within other lists. So that is a pretty good example of a recursive data structure. We're also going to find that recursive structures are absolutely everywhere once we begin understanding this and start looking around. For example, in nature, we have trees. In computer science, we'll have files, directories, and we'll also have data formats, particularly important for this course. So let's take a look at nature for a second. I'm going to come up with a kind of a weird definition for a tree, something to demonstrate recursion. So as an example, I'm going to define the term branch. A branch is a wooden stick with an end, and that end can either contain other branches or it could terminate with a leaf. Okay? So in my example here, I have a stick on the right side. The end of the stick is terminated in 3 more branches, or 3 more sticks. All right, if I continue going, note the leftmost branch here is terminating with a leaf, and the other 2 branches terminate with either 2 or 3 more branches. And finally, I'll get to the point where all of those eventually terminate in leaves. Okay, so here's the recursive part. I've got my definition of the term branch says that the wooden stick is going to split into other branches. So I'm using the definition I'm using the term in my definition. This allows trees to become arbitrarily large, indefinitely, growing. And finally, trees in fact are finite because they must terminate with a leaf. And this is the base case that allows for completion. Please note that down here at the bottom, arbitrarily large is not the same as infinitely large. So there are no infinitely tall trees anywhere. They all eventually terminate. And my definition allows them to have any number of levels of branches, but it also allows them to terminate with leaves at some point and not become infinite. Okay, so I've got 2 terms here. Every one of my recursive functions and recursive definitions will contain both of these. We'll have a base case, something that allows for termination, and we'll also have a recursive case. So in this example, the branch, that allows the next level of depth to be reached. Okay, second example. On your computer, you have a file system, and that file system contains directories. A directory is a collection of files and directories. So here again, we have the definition containing the term. Directories is found in the definition. Okay. So as we take a look, I've got directory A here contains 3 files and 2 more directories. As I think about this in terms of a tree, these files are essentially like the leaves. This is the base case. These are not going to be recursive. I can't have anything inside of these files that's going to extend the file system. On the other hand, these directories are a lot like the branches of a tree, because I can go into directory B, for example, and find that directory B contains another directory and a file, directory C. If I go into directory C, I can look, and that has yet another directory and some files. In this case, keep going. I may have made this example a little long. More directories, more directories. Good enough. Okay, for my final example, we're going to take a look at the JSON file format. And this is a simplified definition designed to demonstrate the recursive nature of these files. So here I have an example of a JSON dictionary. And the term JSON dictionary is actually defined as a set of JSON mappings. So let's go take a look at what that means. A JSON mapping is a JSON string. Here we have name, grade, and score, the keys. And that's going to be paired with either a JSON string or a JSON number or a JSON dictionary. The value, Alice A96. So here I have a JSON dictionary circularly referring up here to the JSON dictionary, which is a mapping. JSON mapping contains the JSON dictionary. So the recursive self-reference here is actually circular. I've got more than one thing involved. It doesn't necessarily have to be direct. And to continue my example, if I add their exam scores to this JSON dictionary, I have a dictionary as my value paired with the key exams. And I can continue this as deep as I want to go. I can break down the exams into midterms and finals. And all of these elements either correspond to the same branches or leaves. So the leaves would be the base cases, and my dictionaries are going to be the recursive case where I can go even deeper into the tree. Okay, so at this point we've talked about recursive definitions and recursive data structures. I'm now going to go into what's recursive code look like. So recursive code is simply a function that calls itself. And that can either be direct, as we see with F on the left there, or it can be circular with functions G and H. And there could be any number of functions that all link back to the first one. It's not necessarily just two functions. So what's this look like in code? It's pretty simple. If we were to define function F, we've got some code. This is going to be a function that actually just calls F, just like it would call any other function. Wrap up with some other code. Same deal with the other side. Circular reference also. I've got a function G. It's got some code in there, and that's going to call function H, just like it can call any other function. And then in the definition of function H, we see we've got some code, and then it's going to call function G. Okay, so one of the motivating reasons why we would ever care, why do we want recursive functions, this seems unnecessarily complicated, is often we don't know how big the data set we're going to be working with is before execution. And in the past, we've dealt with this by using iteration. We've been iterating through lists or iterating through dictionaries to address all of the data. In theory, iteration and recursion are both equally powerful. Any technique that can, or any problem that can be solved with one of these techniques can be solved with the other. However, in practice, one of these is often a lot easier to write than the others. Recursive functions correspond naturally to recursive data. And recursive functions can actually help us reduce big problems into smaller problems. So the smaller problem would be the base case. And if it's a big problem, we want to chop it into a smaller problem by recursing. So in my picture here, I have an example of a professional cutting down a tree. So he's taking it down branch by branch. It's important for safety. If there's a house there, we don't want to hit the house. So it takes a big problem and turns it into a smaller problem. So here we have a small problem. You can chop that up into firewood when he gets it down to the ground. And the big problem still remains, looks like a pretty big problem. It's up high in the tree. I don't know if any of you have ever cut down a tree before. It's actually one of my dad's hobbies. This is a picture of my dad standing precariously on a ladder, 73 years old. This is a bad idea. I was just praying and wanted to get it on video. But there he is taking a branch out of the tree. You can actually see the house in the lower lower right-hand corner of this picture. He lived. He's fine. He didn't fall out of the tree. Don't do it like this. Get a professional. Okay. I've got another example here that works brilliantly in an actual classroom where we have students sitting in chairs. And I'm going to leave the slides in for the people who take the course next year when the plague is ended and we're all back in classrooms. If you want to, you can flip through these slides and take a look. The problem is trying to count the number of students. We have students sitting in rows in a classroom, all bright, smiling, happy faces. And we have the benevolent teacher wearing a top hat, just like I wear every day during class. Okay, we want to know how many students there are. So I'm going to talk to each of the students in the first row and ask them how many students are in your column. Then I can add them all up. Now, because I want to actually stress the iterative nature of solving this problem, I'm going to put some constraints on this. It's dark, so the first student can't actually see the back, so he can't just turn around and count them. You can't get up to walk around and count. You may talk to adjacent students. I actually see this going on all the time in class. And finally, the microphone is broken. So the students in the back can't even hear me. Yet another common problem. So how are we going to solve this? The idea is that we need to reframe the question from how many students are in your column to how many students are actually behind you. This is really the hard part, is how to take a problem statement and turn it into a new definition that allows us to solve the problem with recursion. So reframing is very challenging. So here's the answer. In an actual lecture class, we'd make you guys work through this yourself. But here's the idea. So we're going to ask the very first student. If nobody is behind you, say the number 0. Else, ask the person behind you and say their answer plus 1. So the first student turns, asks the student behind them. This second student actually has someone behind him, so they don't say 0. Instead, they ask them. And so on, and so on, all the way to the very back. And eventually we'll get to the back row where someone says 0. And then, as you can see, it went 0, 1, 2, 3, 4, 5, 6. We're up to 20 already here. So that person's going to tell the person in front of him 20. That person will tell the person in front of him 21. And that student, so on, 22, 23, 24. Clearly, because this student didn't count himself, there must be 25 students in this column. Okay. So as we take a look at this, every single student is actually asking the very same questions. That's the same as each of the students running their very own code. And because each of the students actually is keeping track of a different number, each of the student has their own state. And this is going to be the variables inside of the function. So as another example, we'll take a look at a math problem. And here we're going to be taking a look at factorials. A quick reminder, factorial is just like if I have the factorial 3, that's going to be 3 times 2 times 1. If I have factorial 5, it's 5 times 4 times 3 times 2 times 1. Factorial n times n minus 1 times n minus 2, and so on down to times 1. Okay, so this is actually Tyler's 4-step process to reframing code into recursive functions. I really like it, so I'm going to claim it now as Mike's famous 4-step process for reducing factorials, or reducing problems into Python code. So I like to begin with examples. So in this case, we'll start with some very simple examples. 1 factorial is equal to 1. 2 factorial is equal to 1 times 2 equals 2. 3 factorial is 1 times 2 times 3. 4 factorial, 1 times 2 times 3 times 4, and so on. So I've got a bunch of examples. Now, what I'm going to do is take a look at my examples and try and find instances of self-reference. I'm going to look for patterns. So here's one right here. What I see when I look at the definition of factorial 5, it has a 1 times 2 times 3 times 4 in red, the exact same thing that I saw for factorial 4. And that means that I can replace factorial 5 with factorial 4 times 5. And so on. I see that factorial 4 contains 1 times 2 times 3. That's the definition of factorial 3. So I can replace the definition of factorial 4 with factorial 3 times 4. And so on. All the way down until I get to factorial 1. And that I don't need the pattern. That's just how it is. So when I go back and take a look at writing a recursive definition, what I want to do is convert these examples that refer to themselves, self-referencing examples, to a recursive definition. Here we go. So to start, for factorial 1, I don't really need anything complicated. This is my base case. Factorial 1 is 1. And then I'm going to need a second part for the rest of the numbers. And for these, what I'm going to find is that I have the factorial of 1 less than n times n. This is good for all the rest of the n's. So if I want to turn this into Python code, it's pretty straightforward. Definition factorial n, my base case. And we're going to find that all of these recursive functions have some sort of conditional in them. So if n is equal to 1, just return 1. And then if it's not actually equal to 1, I continue on with this function and compute a partial value, p, and that's going to be equal to factorial of n minus 1. So we'll get that partial result. And then we will return the final definition, n times my partial result, p. Okay, let's run it. And by run it, what I really mean is look at lots and lots of PowerPoint slides that go through an example and break it down into steps. Okay, so as we trace through this, I've got my function over here on the left so we can see it. And at this point, I don't have a stack frame. What I've got is a different kind of mental model to trace through the code line by line. But I've got some boxes in there that look like frames that we'd see in a stack that keep track of variables. So there are some similarities. So at this point, somebody has called factorial 4. The very first line of factorial is if n equals 1. So I've got up here, I'm going to do this test, if n equals 1. That is not true. So we're going to continue down to the p line and compute a partial result. Now remember, when Python is going to assign a value to a variable, the first thing it does is it takes everything on the right side and simplifies it to actually get a number or data that I can store in a variable. So in this case, I need to call factorial of n minus 1, and n here is 4. So 1 minus n minus 1 is going to be 3. So we call factorial with n equals 3. And I've got a new box to represent that second function invocation. So I jump into this. I've got n equals 3. First thing I do is test if n equals 1. That's not true. So we'll skip ahead. And now I'm going to try and assign a value to p. Remember that the very first thing Python does in an assignment is try and simplify the right-hand side into a value that it can store in a variable. And to do that, it needs to solve factorial of n minus 1, or 3 minus 1 is 2. So it's going to call this function yet again. And I've got another box there to represent factorial with n equals 2. So very first line of the factorial function is n equal to 1? It's not. So we skip ahead, and now I need a new partial result. To solve this partial result, I'm going to call factorial with 2 minus 1 is actually 1. So I've got a new function in invocation. So factorial n equals 1. We jump up to the top line of the function and say, is n equal to 1? Yes, it is, finally. So we're just going to return 1. So I've got a return value. That return value is going to go into the p value of the previous function invocation. Okay, great. Now I can continue with my third function invocation, the one where n was equal to 2, and I can return n times p, or 2 times 1, and that's equal to 2, so we're going to return that. Okay, that return value, that 2, is going to go into the p value for a function invocation with n equal to 3. So here we go, p is now equal to 2. In this box, the sort of more bold one, all right, now remember that n was equal to 3 in this function invocation. P is equal to 2. The product is 6, so I'm going to return that product, 6. That 6 is going to be stored in the p value from the function invocation with n equals 4. So p is equal to 6. I know that n was equal to 4, so my return value is their product, 24, and we're going to return 24. Okay, so one of the really confusing things for students is I've got all of these variables with the same name. I've got 4 n's here. I've got 3 p's. How does Python keep these all sorted out? And how do we keep them sorted out when we're thinking about these kinds of problems? The answer is frames. So in a recursive function, each function invocation has its own frame. That's where we store variables. So each function invocation got his own set of variables, and they can reuse the names. But what we're going to find is that every single invocation of a function is going to use the very same code. So variables live in frames, and those frames are stored in stacks when we run the actual code. And what I want to highlight here is there's actually only one active frame at any given time. So as I continue to do factorial n equals 5, n equals 4, n equals 3, 2, 1, and so on, there's only one active frame. And the rest of these frames are waiting for the active frame to finish to get a return value so they can do something with it. When a function invocation reaches that return value, it's popped off the stack. The return value is sent over to the next active frame, shown there in red, and so on. So the bottom frame will always be the global one, and then the rest of these will be function invocations. And we may have multiple function invocations for the same function simultaneously. And again, only one of these is active, the rest are waiting. So let's take a deep dive at the runtime stack and take a look at what's really going on. In this case, I'm going to be calling Factorial 3 for my example. I've got the code there for review in the upper right-hand corner. So when we first begin any of our programs, we're going to find that we have a global frame. We'll keep track of global variables here, and then in this frame, we'll be calling Factorial 3. So the moment we call that, we're going to get a new active frame for the factorial function. This is going to have two variables in it. We're going to start off with n is equal to 3 in this case, assigned as a parameter, and eventually we'll be adding a p variable. There it is, but we don't know what number to put there yet. We need to actually go and call factorial with n-1 or factorial 2 to get the answer to store into p. So at the next time step, I've added a new active frame for that factorial function call with n equal to 2. And again, similarly, that'll have its own variable n and its own variable p, but we can't assign that p until we actually simplify it and call factorial n-1 or factorial with 1. In this case, we don't need a p variable. It's going to instantly return 1 after that conditional statement. And that return value 1 is going to be stored in the variable for p of the second invocation down, the second frame. And as soon as we've done that, we can eliminate the factorial n equals 1 frame. That's destroyed, it's gone forever. But the return value is stored in the variable p for that function invocation. Similarly, we can then do some math, compute a return value, in this case 2, and that will get stored in the variable for p for the next function invocation down the stack. And again, we'll destroy that function invocation for factorial with n equal to 2. And finally, we'll compute factorial 3. P was equal to 2 when I stored the return value here in this function invocation, a different p, and we'll return 6 to the global frame where we can do whatever we want with it. Okay, I want to just take a second and address two really common infinite recursion bugs. So let's take a look at what happens if, for example, I call this particular factorial function with a negative number. In this case, I'll have factorial n equals -1. It's not equal to 1, so I'm going to compute factorial n-1, or -2. It's not equal to 1, then I'll do -3. It's not equal to 1, then we'll do -4. And this is never going to terminate. It's going to continue going forever. I've actually got this. Let me slide this over. There we go. Hope everyone can see that. I've got Factorial here defined. It's currently running Factorial 3. Factorial 3 was 6. We just did that in the previous slide where I actually many slides. And if I go ahead and put in -1 here and run this code, it's running the code down there at the bottom. You can see that. This actually returns an error. For Python Tutor, we get a server error. Your code might have an infinite loop or be running too long. In this case, this kind of error is called a stack overflow, where I have called this function so many times, any -1, -2, -3, and so on. Each of these function invocations takes up memory. It's got its own n variable, they've got their own p variable, they reserve space for those, and eventually we run out of memory. So we technically can't have an infinite loop with recursion. All right. It doesn't actually tell us this is a stack overflow error in Python Tutor, but that's the type of error we're getting. Okay, if we go back and take a look at a second type of recursion bug that's really common, What if we forget what happens when we put in the n equals -1 check? If we don't have a base case, if the only option is to recurse, this is also never going to finish. So in my global frame, I'm calling factorial with n equals 3. There's no check. I just call factorial with n equals 2. And then 1. It doesn't stop here because I forgot my terminating base case. N equals 0, n equals -1, and so on. And this will continue forever until my computer runs out of memory. Also, there we go, never terminating. Okay, I'm going to pause the video, go get some Mountain Dew, and be right back with some coding demos. Alright, I'm back. I've got my microphone switched over to directional mode, so hopefully you guys won't hear too much of the keyboard clicking this time. And I want to take a look at some coding demos. For my very first demo, I'm going to be looking at printing nested lists of lists as bullet points. It's pretty common. A lot of word processors do this. So what we'll have here is a list that contains lists of lists, and I'm going to print them out so they look like this, where the top level of lists is shoved all the way over to the left, and then each of the sublists is indented, and we'll put stars on all of them because they are bullets. Okay, let me switch over to Jupyter Notebook, and we'll get started. Frequently we find that functions that change the formatting of a way the data looks are called pretty printing. So I'm going to do the same thing. And in pretty printing here, we have a list of items that we'll be printing out. Okay, and just to get started, I'm going to print items just so I've got some code here and I can make sure that I didn't forget any dumb syntax that oh, let's check this out. Got a colon right there. Okay, and then I'm just going to create a list. We'll call these bullets. About bullet points. This is going to be a list, so I've got square brackets, and let's just start off with 3 things in here. We'll go with A, B, and C. All right, and then we will call this pretty print bullet points. There we go. Let's see what this does. There we go. Perfect. It printed off A, B, and C for me. Now, in my example, I really would prefer that they were on their own line, so let's take care of that next. To do that, I'm going to iterate through all of the items in the list. For I in items, I remembered the colon this time, genius. I'm going to print them out. See what this does. There we go. Flatten my list. Okay, at this point, I'm going to go ahead and add another, let's actually put the star in right now. So go ahead, we'll do star plus I, and try that out. There we go. Now it has a star. Now I'm going to upgrade this a little bit. I'm going to go with a more complicated example, and I'm going to add another list inside my list. So we'll put in 3 more items, and let's go with the numbers 1, 2, and 3, and try running this. Oh, right away we see we get a type error. Okay, turns out that down here, my error is that I can only concatenate strings to strings. So right here I'm trying to add a string, the star, to a list, my 1, 2, and 3. Okay, so this isn't going to work. Now we do know that we can print out lists. I did that in the very beginning. I'm just going to change this to a comma, and now I should be able to print out all 3. Excellent. I've got A star, B star, and my whole list here. That's not exactly what I want. I also see that it added a space for me. I'm going to go ahead and remove the space by putting a blank separator in. There we go. All right, so the next thing I need to do, I know that I can print out lists like that. In fact, pretty print. I'm just going to copy this list directly into here and demonstrate that it does in fact work. So what I need to do is when I get to this list item, so it'll print I will first be A, then I will be B, and then I will be a list. I need to know that this is a list and actually call pretty print again on that item. So let's go ahead and test to see if I is a list. So I need type of I equals list. If that's the case, then I want to do something Right now we'll just skip them, else we would like to print them out as bullet points. All right, let's try this. It should just skip the list at this point. But I've messed up. Ah, here it is. I forgot the colon. We just add that back in. Most common mistakes that I make is punctuation. Okay, so now what I find is that I have indeed skipped the list. Now, what I'd like to do here, instead of just passing and skipping the list, is actually call pretty print on my secondary list. Let's take a look at this. Excellent. So now I'm printing out all of the items on their own line from my secondary list. And in fact, if I add a third list, let's put one right here, inside of my second list, let's go with I, J, K. I should find that this also prints I, J, and K in the middle. So I've flattened my list. Okay, so the next thing I'd really want to do is add some indentation. I don't want a flat list. I want these to show the level of indentation. So when I print them, I'm going to need some spaces. Oops. I don't know how many, so I'm going to use a variable. In this case, I'm just going to get this started with spaces equal, we'll put 2 of them in, and that should, let's put a bunch in so we can actually see that all of these jump over when I do that. Okay. Now I want the number of spaces that I've added to be dependent on my level of indentation. So I'm going to take spaces, I'm going to multiply those times a variable that will contain the level of indentation that I want. And I'm going to start us off with indentation equal to 0. I don't want to move it over for the top level at all. So let's run this. There we go. I didn't make any typos yet. Let's try calling this with not just the default value, but with 4. Run that. All right, interesting. So it appears that for the very top level, when I call this indent variable will be 4, and it's printing out A and B with the correct indent level. But when I call pretty print again, the recursive version, what I'm finding is that it's not actually using my indent 4, it's reusing the default value. So I need to go back and call this pretty print and give it my parameter indent so that it cascades all the way down. Now what I should find is that I'm using an indent level 4, there we go, for all of the items. Now that's not exactly what I want. I want to indent more and more and more every time I call the function, every time I have a new level of nested list. So I'm going to say that indent plus 1 in this case. And then we'll go back and start it out with level 0. And now what I should see is that each of these levels get indented a little bit, more. Let's go with 3 and see. That should make a more dramatic looking nested list. Okay, so what I'm doing here, if I just walk through, from the top level, I've got a list. It's going to go through and take a look at these items. It's going to grab I is equal to this letter A. It's not a list, so it's going to take my number of spaces. Indentation level at the top level was 0, so it's going to print out 0 spaces, and then my bullet point, the star, and my variable A. The variable I with the value A. Next thing it's going to do is go through and do the same thing with B, and then when it gets to my third iteration through the list, it's going to find that I have this list with 1, 2, another list, and then 3. So it's going to go through and call pretty print again on the list. And it's going to call indentation with not 0 now, but with 3. And then it's going to go through that list for I and items, and this is a second I, so it's going to get the number 1 first. That's not a list, it prints it out. But it's using indentation with 3 spaces, then the star, then the number. Then we'll do 2, and then we get to yet another list. So in that case, this if type is equal to list is true, and we call pretty print again with this item, just this, tertiary list, and indent now will be 3 plus 3, or 6. And then when I go through this list with I, J, and K, what I'll find is that when I is equal to the letter I, it's not a list, so we print it out with 6 spaces, and then it'll go through and print J with 6 spaces, and so on. when we finally return from that function, it'll go back and have this list where I will now be equal to the number 3. Indent in this function invocation was only 3 spaces, so it prints 3 spaces, 1, 2, 3, and then the number 3. And that will end the second function invocation. We go back to the very first call to pretty print, where indentation was 0, and it'll wrap up printing out C. Alright, I'm back with my second example. You guys have no idea how much I love being able to go grab some Mountain Dew, cough a whole bunch, recover, and jump right back in. Okay, for the second example, I'm going to be using a list of numbers, and I'm just going to be testing to see if that list of lists of numbers contains a particular value. So I'm actually going to go, my function will be called contains. I'm testing if this list, there's the bracket, contains the number 3. It's a list that's got 1, 2, another list, 5, 6. And in fact, the nested list here does contain the number 3. So this should be true. All right, I'm going to jump into Jupyter and have a go at this. So first, I'm just going to copy this line. I'll pop over into Jupyter Notebook. And this will be the test I'm going to run. This should totally fail until I write a function. Definition contains. It's got 2 variables. I'm going to have an n, and I'll have a list of numbers. Remember the colon. And let's just print numbers just to make sure this is working. Actually, we'll print them both. We'll print n and numbers. And there we go. Printed them out. Perfect. So that's not actually what I want this function to do. What I really want to know is if it contains that. So I'm going to go through each of the items in numbers. So let's see here. Let's go for I'm already using n. I would normally love to use n there. For I in numbers, if n is exactly equal to I, remember the colon, what I'd like to do, it found it. So we'll just return. Return capitalized true. If we don't find it, then after it goes through all of the items in the list, all of the numbers or lists, we will have it return false. Okay, let's give this a try. All right, and we see as it's gone through, this is actually returning false. It's looking for the number 3. Let me add one more line of code, and I want it right here. We are testing item I in this case. So it goes through. First thing it does is it's testing the first item in the list, which is a 1. That's not a 3. It continues. It's testing item 2. That's not the number 3. So it continues. Now it's testing this entire list. This list right here is not the number 3. So it continues. And then that's the final item in my list. All right, so let's try this running one more time. Instead of contains 1, let's try contains 2, just to make sure we have a positive example. So run this. It tests item 1. That's not a 3. Oh, I'm sorry, 2. Then it tests the second item, which is a 2. It is a 2, so it returns true. All right, so excellent. So I'm going to change this to 3 again. Now what I really want to do here is not just test the top level, but actually go in, and if I find out that I've got a list, what I'd like to do is call contains one more time on that sublist. So let's go ahead inside of my testing all of the items. I want to know if this I is a list. So if type of I exactly equal to list, then what I wanted, let's start off with just printing it. Print I, else in this case, if I is equal to 1, we'll return true, otherwise false. And I'm going to go ahead, I do want that testing item I right here. All right, let's make sure I didn't make any typos. So here we go. Testing item 1, 2, the giant list. And then what I did find is that this is actually a list, so I printed it out again. All right, not exactly what I want. What I'd really prefer to do is call my function contains on the second list. So I've got contains n and items I. Or item I. All right, let me try this. So now we are looking at a recursion. So I'm testing item 1, 2, my list, but then I'm calling contains again, and now the first item in that list is a 4. Then I've got a list here, so it's going to call contains yet again and test the first item, 3, a list of 3. And then because it's a list, it's going to call it again and look at the only item in that list, test the 3. That should actually return true right there, but I didn't do anything with it in this contains line. It's not doing anything. It's just ignoring it. So it continues on. The next item in this list was the list 8 and 9. So we're going to go through that list, 8 and 9. Then we go back to this secondary level list and test 5 and 6. Okay, so this looks like it's actually going through and testing all of the values, but it's not actually stopping when it finds the 3. So what I'd like to do instead, right here, if this contains function is actually true, then what I'd like to do is return true. Otherwise, we can just keep going. All right, let's see if this fixes my problem. Excellent. So as soon as we found the 3 right here, this is going to return true. And that's going to return true to the next level up function that called with this list. And okay, forgive me. I just took a little break to cough a whole bunch. And I'm feeling a little better now. Okay, so what I found is that when I got to this when I got to the item 3 in this nested list, it returned true. And that returned true got passed up to the previous level to the if contains, and that returned true. That returned true got passed to the level above that, which was calling if contains, and that returned true. And finally, at the very top level, we were passed true to this contains, and the top level returns true. All right, let me just test some other things here. In fact, for I in range, let's go 0 to 13. Now let's print first I, and then we'll print out the result of this function contains. And I've got a lot of stuff printing there. Let me take this one out. I don't need to know what I'm testing anymore. I just want to make sure this works for all possible cases. Let's try this again. Okay, so looks like I still have a little bit of a problem. This list does not contain true, and yet my function is returning true. That's because I forgot to change this 3 to an I. I want to be testing all of those numbers, not testing 3 12 times. Okay, so this is starting to look pretty good now. So when I test it with 0, 0 is not anywhere in this list. It returns false. When I test 1, it's right there, true. 2, right there, true. 3, 4, 5, 6, all true. There's no 7, so 7 gave me false. There is an 8. There is a 9. So those are both true. And 10, 11, 12, all false. So this is looking pretty good to me. I think I'm going to wrap up right here. Have a great day, everyone. And I will be coming back to you on Friday. Mina's got Monday and Wednesday lecture. If you have any questions, go ahead and post them on Piazza or come find us during our office hours. Office hours are now online using Blackboard Collaborate. To get there, log into Canvas. Blackboard Collaborate is one of the options on the left. During office hours, there will be a session there that you can enter. You'll go into the common area. I forget what it's really called. And when it's your turn, just post something saying, I'm here now, I have a question. My partner is, Bob. And one of the TAs will pull you into a small group breakout session where you can then share your screen, show the TA what's going on, ask any question you like. And if the TA does not appear to be currently available, if they're in a breakout session, I don't believe their name shows up in the common room. Just be patient. All right. Thank you for listening, and have a great day.